So originally this kind of started out as a talk about drought primarily, but it morphed pretty quickly into a climate change discussion, mainly because the two are pretty interlinked. So we've got two birds here that I'm gonna highlight throughout basically highlight about the bird-centric portion of the talk. We've got greater sage-grouse here and our state bird, the lark bunting. So just kind of an outline about what I'm going to discuss. I'm going to start off with the forecasted and observed changes in Colorado's climate, just kind of highlighting some of the things that we've seen change pretty quickly in Colorado, particularly in the past 20 years. And then I'm going to dive right into what those effects are on Colorado's birds. And I'm going to highlight some of the tools that are used to make predictions about what some of these effects are, as well as what some of the observed effects are. Audubon has a really useful web page where they have, you can basically go look state by state, species by species, and see what some of those effects are. In particular, I'm going to highlight the lark bunting, the American robin, flammulated owl, and the greater sage-grouse to talk about some of the specific things that are both have been seen and observed, the effects of climate change, as well as kind of what some of the projected effects are. So as mentioned before, I was trying to use as few graphs as possible, but I can't help myself. So, so this is one that probably everyone has seen. It's kind of the observations and projections for temperature changes in Colorado. And if you kind of look sort of at the two-headed snake here over here to the right side of the graph, we have two different scenarios. We have a lower emission scenario and a higher emission scenario. And one thing to point out on this graph is that pretty much since the year 2000, we haven't hit any sort of we're above the average for the previous 100 years. So it's definitely, there's a large increase that's happened in the past 20 years. It's projected to go even higher. It does seem like if we were on the lower emission scenario, we might be seeing some leveling out by the end of the century. But unfortunately, things seems like we're trending towards this higher emission scenario. Most of the world, if you look across what all the projections are, we're definitely trending toward the higher end of most of the projections. And I'll kind of throughout the talk about some of these different projections. Audubon uses 3 different scenarios. So we'll go through some of those just to look at what the effects are. For each scenario, there's a more severe effect going from lower to higher temperatures. It's not just average temperature. If you look at the nighttime temperature is also increasing. For those of you who are native to Colorado, you probably have a much more experience with this, that laying in your bed at night thinking how hot it is, so it really is that hot. And this also has a big effect on drought conditions, since you're not even getting a reprieve during the evening, it's keeping those temperatures higher and it's causing more drying. So even in the absence of higher temperatures, those warmer temperatures at night are really having an effect both on those drying conditions and the number of air conditioners that are sold in the local area. So here it says in Denver, the average nighttime temperature has risen by 1.8 degrees since 1970. It's 1.7 degrees warmer in Colorado Springs and 0.3 degrees warmer at night in Grand Junction on average. So even in a place that's really dry, where you would expect that temperature to drop quicker, like on the west slope in Grand Junction, even they are seeing increases of nighttime temperatures. So I'm going to go through a series of maps here, looking at projections of annual temperatures by 2050 across the Western United States. And kind of one of the takeaways from this that I want you to get is there is some uncertainty about how that temperature is going to change. So on the left-hand side, we kind of have the average of what all the projections are. So when they run climate models, like a lot of statistical models, it's not just one model. They do thousands or tens of thousands of iterations under different scenarios, looking at sensitivities to different variables and sources of data. And then they kind of average them together. And so that's what you see on the left-hand side. So that's all the projections kind of averaged together. And even there, we're looking at a 3 to 4 degree temperature change for most of eastern Colorado, and a 4 to 5 degree temperature change for the west slope. And then kind of if you look at all of those models that they run, if you look at the warmest 20%, we're looking at a 5 to 6 degree temperature increase. And then if you look at all those models at the coolest projections for increase, we're still at a 2 to 3 degree temperature increase. So even the most conservative on the far right is forecasting a pretty big increase. Similarly, we can look at annual precipitation change by 2050. The average projection has an overall slight increase in precipitation change, a 0 to 5% increase. But if you look at southern Colorado and a lot of the Southwest, it's forecast to get a lot drier. If you look at some of the wetter outcomes of some of those models, you do see that there is potential for an increase in average precipitation. But if you look at the driest ones, again, that southern part of Colorado shows up. So that's probably a pretty good indication that there's some consensus there that the southern part of Colorado will most likely end up being a lot drier on average. So if you're confused by those maps, this is basically all the maps in one spot where you can kind of just look at the warmest and the coolest runs and all the projections averaged, still seeing those potential for large increases. There may not be a big average change, again, just looking at these precipitation maps, but there does seem to be some sort of trend, again, in southern Colorado. So what does this really mean for Colorado? So you can look at the temperature departure graph here on the right, and you can see that basically since 2000, we've had almost no measurements that were below average. You've got, it looks like maybe 2009 was slightly below average, but all the rest of those years since 2000 have been above average. And I like what it says here in the second paragraph. This is from a climate report for Colorado. It says, you may be asking, it's only 2 degrees. What effect does this really have? So historically, that large of a temperature change took place over thousands of years, not just in a few decades. And I think that is kind of the take-home message for birds, is that, birds are used to, there's enough genetic diversity in most bird populations to adapt to some sort of change in the climate. But when this takes place, what typically takes place over thousands of years is now going to take place probably within the next 30 to 70 years. That is going to be a big disruption to birds. And birds are going to move around, and some of them are going to adapt, but others are going to have difficulty adapting. So I'm going to talk about kind of some of those things in a species-specific way here in a minute. So it's not just temperature and precipitation, it's snowpack, so it's stored precipitation too. And I like this graph up here about the number of frost-free days by decade in Aspen, Colorado. So you can see from 2010 to 2018, there were 120 frost-free days. So you're talking about a month, an additional month of frost-free days, basically since the 50s and 60s. So that's a pretty big difference. And a big change in the growing season, and that has going to have a substantial effect on birds. Just checking the chat here. And then if you look at overall snowpack across the entire state, here in the lower right-hand corner, you can see that most of those dots are red, indicating decreases in snowpack across the average from 1955 to 2015. So there's a couple of blue dots buried in there under where Rocky Mountain National Park is, but other than that, there's either been no change or mostly negative changes in snowpack. So that has a big influence, especially when we're talking about things like wildfire. So I couldn't find a good graph for Colorado, but we know that large wildfires are increasing across the entire Western US, especially recently in Colorado. We know we've had some of the largest and some of the most destructive wildfires in Colorado history just in the past 2 to 3 years. And that's been after a very active wildfire decade from 2010 and on. So that's only going to continue. Lack of cold nights. I don't know if some of you were on the Fort Collins talk last week. He spoke about how lack of freezing temperatures increases pine beetle infestations. We've already seen a big effect of that in Colorado, and that's only going to exacerbate the wildfire problem that we're having. And with those big wildfires comes huge transformations of giant tracts of habitat that take a really long time to recover. And you can just look at the sides of the hill in Colorado Springs, and not much has changed up there in 10 years. I mean, some of it is recovering, but it's not recovering very quickly. This is the biggest issue, I think, for birds, especially in the plains, is this mega drought, the concept of mega drought. So mega droughts aren't your average droughts. These are droughts that last 20 to 30 years. So the Western US obviously is prone to drought, just geographically, we're kind of in a spot where, all the stars and clouds have to align just right so that we get good regular precipitation. So we have a lot more annual variation in our precipitation than locations that are closer to the coast. And then if you look at sort of a multi-decadal precipitation, we do have these big changes in drought. And so a 10-year drought in the West is not something that's really out of the ordinary. It can be kind of catastrophic in some ways, but it's something that's occurred pretty regularly in the Western US. But for a mega drought, something that lasts 20 to 30 years, it's not that common. So the current likelihood of a mega drought in the Western US is about 12%. If greenhouse gas emissions stop increasing by mid-century, the likelihood of a mega drought is still greater than 60%. If they continue to increase along the current trajectories, then there's an 80% chance of a decades-long mega drought between 2050 and 2099. And this animation here, I think, kind of helps drive home the changes in soil moisture that have occurred basically in the past 150 years and that are projected to occur this century. So you can see this is actually, it's looking at soil moisture, so it's not precipitation directly, but again, right around 2000, the year 2000, you start to see that shift. And by the year 2095, you see a pretty big decrease in soil moisture across most of the Southwest and actually a big portion of the Southeast as well. And that's going to really drive changes, I think, in bird distributions and bird populations that, in particular, in those especially drought-prone areas that are at lower elevations in the Great Plains and part of the desert Southwest. So shifting quickly to birds, the first thing I kind of wanted to show everyone is these tools that I can put the link to these in the chat here at the end. There's vulnerability assessment tools that Audubon has created, and they kind of divide them up into different groups of species. So you have the high vulnerability species. In this case, that's what I'm going to focus on. And then you can do it by location. So this is for Colorado, even though it doesn't specify in this screen capture that I got. But under a 1.5 degrees C increase, they've identified 7 highly vulnerable species, as well as 77 moderately vulnerable species, 74 low vulnerability species, and 83 that they think will remain stable. So I'll circle back around to this. It's not all bad for all birds, but there are a lot of birds that are impacted. So you've got 7 at the 1.5 degrees C scenario. When you bump it up to 2 degrees, the number triples to 21 highly vulnerable species. And then when you bump it up to 3, you jump up to 62. So each of these temperature scenarios kind of represents a different set of species that are vulnerable. And unfortunately, it does seem like we're more than likely headed to that 2 to 3 degree increase. So when you think about what some of the expected effects of climate changes are to bird populations in Colorado, I've kind of narrowed it down to 4 things that I think are important. These aren't the only 4 things, but these are like 4 of the biggest ones, at least in my opinion. The first effect is the direct effect of habitat loss and habitat transformation. So this is going to occur because of direct shifts in the biome, because in the southern portion, for instance, of the grasslands, in the Great Plains, a lot of the area, it's just going to become too hot for a lot of those grass species to survive. You're also going to have that increased chance of severe drought, which is going to really shift both the plant community as well as the bird community. And it's also going to increase the probability that fire will become a big factor in a lot of those areas. And some of these places were historically maintained with fire, both in the Great Plains as well as in the mountain regions. So that the fire itself may not be the factor, but the intensity of the fire and the extent of the fire, like how many acres those fires burn, will be a big factor. The second thing that's an expected effect of climate change is sort of this effect on what's called phenology. So phenology is essentially, it's like nature's calendar. So it's when trees bloom, and I'll talk about more of this in detail in a minute, when birds start singing, when birds begin to migrate, either arriving or departing, as well as when they start breeding. And climate change is expected to advance some of those dates. So earlier breeding times, earlier migration, and those types of things. So I'll talk about kind of some of the things that have been observed with birds in Colorado related to that. There's also a potential to influence survival and fitness. And here I have reduced, and that's not necessarily true for all birds. It might increase survival and fitness of some birds, and it probably will. There'll be some positive effects for some species, but for species that are negatively affected, we're probably going to see reductions in survival and fitness. And fitness just means the number of offspring that these organisms produce. And the last thing is kind of one of the bigger ones, is that we're going to see range shifts for a lot of these species that go northward towards cooler temperatures and cooler latitudes, and then an upslope migration of some of these birds. Some of this depends on whether or not there's suitable soil types upslope that'll have similar characteristics to the existing habitat down below. So some of these birds may not be able to migrate upslope, or they'll have a limited ability to move upslope just because the habitat is going to have difficulty kind of chasing that gradient, that temperature gradient and moisture gradient to move upslope. So an example of that is greater sage-grouse. We do expect that some of that sagebrush habitat is going to be able to migrate a little bit, but there's a lot of barriers to that migration. It can only go so high just based on soil type and conditions. And I'll show you an example kind of where that's probably going to occur, primarily in some areas in Wyoming and some portions of Colorado as well. So I thought I'd start with lark bunting because lark bunting's a species I think a lot of us have a little bit of experience with. Either we've seen them or we've gone looking for them at some point. And they're pretty interesting in that they're one of these species that kind of shifts its range year to year already. So it's already moving around quite a bit. And it's looking for places where there's been recent rainfall. So it's kind of a good bird to look at because we know quite a bit about it, and it might not be that hard to predict where it goes. Plus, it has some ability to move. So this is basically the current predicted range of lark bunting in Colorado. You can see that most of its range is in the plains on the eastern half of the state, but there are some places where they show up, like in the San Luis Valley. And there's a couple of other places on the west slope where they occasionally show up at higher elevations as well. So kind of stepping through this again, like we did with the example earlier of the different scenarios to look at the different species. So instead of looking at the number of species changing that are sensitive, we can just look at the range that's lost or gained by these different scenarios. So at a 1.5 degree increase, you see that at the periphery of the range of lark bunting, that's where you start to see the effects first, which makes sense because that's typically a lot of times at the southern portion of the range, or maybe it's marginal habitat out at the edge of its range. So you see some movement up. So you sort of see this worsening scenario coming from the south, but you see a few gains in potentially better habitat even in some of these interior areas in Colorado. At a 2 degree increase, you see it gets slightly worse. And then a 3 degree increase, you can see that a lot of that habitat is no longer suitable and is pushed farther north. So how do we know some of this information about how some of these birds are going to respond? Lark bunting, as I mentioned at the beginning, there is quite a bit known on it. And so the Bird Conservancy of the Rockies has done some really intensive bird surveys kind of across the West. And this in particular is going to focus on 3 different bird conservation regions. So this is bird conservation region 11, 17, and 18. So at the northern end of its range in the lower 48 anyway, is the prairie pothole region. And that is kind of a decent habitat, but kind of getting at the margins of their northern range. Then 17 is the short, or 18 is the short grass prairie, and 17 is the badlands and prairies. And what they do at these surveys, they basically set up a grid of 16 sampling points and kind of like, I think it's like a 1 kilometer square. And they sample those really intensively. And then they've done this for over a decade now. So it doesn't have quite as much data as the breeding bird survey, but it has some extra features about their sampling design that are a little bit better than the breeding bird survey that's been going on since the 60s. And then they can look at kind of the dynamics of where these birds show up during some years and where they aren't in following years. So we've always kind of known that there's something going on with rainfall with lark buntings, and that drought has a negative effect on their choices of where to breed on an annual basis. So I've kind of tried to this did have a graph on it, by the way, and I took it off, so you should be proud. They looked at satellite imagery, and they looked at whether or not the area where their sample point was taken was green compared to the other areas around it. And so there's a certain way you can look at reflectance from vegetation, and you create something called a normalized differential vegetation index. It basically says, is the patch that you're looking at greener than the areas around it? And what they found is that, sort of unsurprisingly, that green areas that are greener, that are grasslands, are good lark bunting habitat across multiple years. And that's sort of the key. So places that receive regular rainfall, those birds will stay and breed in those areas multiple years. So that sort of supports this population stability, because the birds kind of know where to go back. They're making assessments about habitat quality based on this greenness. But in areas that maybe they bred one year and then it was sort of drought type conditions the following year, they abandoned those years. So just by way of animation here on the left, you have a lark bunting that finds green habitat, breeds successfully, and then the next year it's going to come back to that exact same spot, or that same patch. Now, it's interesting with lark buntings, this is kind of an aside, that they don't have a lot of site fidelity as an individual. So there's not like some neotropical migrants, for example, will come back to the exact same territory year after year after year. Lark buntings aren't necessarily like that, but they'll have these big populations of birds will occupy the same patch multiple years if there's green vegetation around in suitable habitat. But if it's green one year and then brown the next, the birds typically don't breed in those same areas. The other thing that they've looked at, and this is in Colorado, they've looked at how temperature and so heat directly and the number of dry days during the breeding season affects nest success. And they haven't just looked at this in lark buntings. So if you remember from that list, the vulnerability also included chestnut collared longspur and McCowan's longspur. And for those species, in addition to western meadowlark, they found that nest success decreases as that heat increases and the number of dry days increases. So there's a direct effect to reproduction based on that heating, both directly with temperature and the number of days during the breeding season. They've also found in lark buntings that drought has a strong negative effect on fledgling survival. So even if they were able to breed successfully and those birds fledged from that nest, those birds actually had lower survival, which kind of makes sense during a drought than they would during a wet year. And that's probably related to both the things that were in those other studies, heat, number of dry days, as well as food availability in the form of grasshoppers or other types of insects that are available to feed fledglings. So sort of anecdotally, I kind of thought back to some observations that I had personally during wet and dry years in Colorado. So I thought I would just look at eBird data during wet years and dry years. So in 2016 was a relatively wet year. In 2018 was a pretty dry year. And if you just look at lark buntings in Pueblo and El Paso County, you see some pretty big differences. At first you look at the height of that graph, and eBird kind of does a weird thing where it won't let you manipulate the axes. But if you look on the graph on the left-hand side, on the x-axis with birds per party hour, it's at 100. So in May, there was someone who was recording over 100 birds per party hour in 2016. If you look at that same time period in 2018, you're talking about a little over 35 birds per party hour. And the other thing to kind of look at is that in 2018, there weren't a lot of birds around during what we consider the core of the breeding season. So beginning in June and running through July, and even August. Sometimes lark buntings will breed later. So there's this big dip. And then once you get to September, you see this spike again in 2018. And that's probably indicative of fall migrants of starting to come through, as we see around here a lot. Even if we don't have a lot of breeders, we typically get fall migrants that are starting to move back south. So just even in regular birding data on eBird, you can see some additional information about lark bunting's aversion to drought conditions. And it's not just lark buntings. So you can see the same thing with grasshopper sparrows in Pueblo and El Paso County. The differences aren't quite as stark, but I remember in 2016 doing bird surveys and thinking, you know, there's grasshopper sparrows in places that I wouldn't even have expected to see them. And they're more frequently encountered than I thought they would be. And then in 2018, a lot fewer grasshopper sparrows seen during the breeding season, especially. So that's kind of the summary of direct habitat effects and kind of how we've, folks have linked those changes in survivorship of like fledglings, changes in productivity of nest success, and how those types of things are going to directly affect where those birds need to move in order to survive and produce offspring. So as we encounter more droughts, as there's more, as the temperature increases, then those birds are going to have to shift to areas where they can find conditions where they can be successful. The next thing I wanted to talk about is phenology. So this is the timing of breeding and how the timing of breeding or migration might influence survivorship, producing offspring, even if there isn't necessarily a shift in the habitat. So as I mentioned before, phenology is basically nature's calendar. So this is when plants bloom, when birds start to build their nests, when migrants arrive and depart. There's a whole organization that tracks all of these things, where you can enter in the first time you saw a certain insect emerge, like a butterfly. You can say when you saw certain flowers start to emerge, when certain trees start to leaf out. And they're tracking all of this information. And there's sort of remote ways you can track some of this. So they track green up of trees across the US using similar technology as the NDVI, the Normalized Differential Vegetation Index, is sort of the same type of data that they use. So they can track and see when things green up and if things are greening up earlier during certain years or later. But I like this quote from a paper that's kind of examined phenology across different species. Survival and reproduction often depend on the timing of life cycle events. And the rates of survival and reproduction also directly affect population dynamics. So whether the population is increasing, whether it's decreasing, how many individuals are surviving to become an adult to enter the breeding population. So therefore, phenological shifts caused by climate change could affect population persistence. So if this timing is disrupted somehow, whether it's migration timing, nesting timing, then that can have effects on the population. I'll try to explain that more here in a second. But for birds, a lot of this timing is dictated by day length. So day length has been shown to trigger when birds migrate. It's been shown to trigger when birds start singing. So if you think about like great horned owls, we know they start hooting kind of in midwinter. And then for some reason in the fall, all of a sudden you start hearing them again. And that's because there's a similarity in the day length in the late fall that kind of triggers something in there to start being territorial again. Now they're not going to go into full-fledged breeding, but you also hear that, similar things with other birds. You won't have heard certain birds sing, all summer after breeding season has stopped, and then suddenly you start hearing a few for a short window in the fall. And that's because that's triggered by day length. So kind of keep that in mind, because if day length is constant, so it's the same year after year after year after year, and if a bird is using that to try to determine when is the best time to depart, to migrate, when is the best time to arrive on the breeding grounds where they know the resources are going to be available, then that's kind of a moving target for them. So they're going to have to rely on different cues other than day length, which they do to some extent, but it can cause issues. And so one of the first, or one of the more famous, I should say, examples of this was published, I think in the year 2000 or 1999, and it was from the Rocky Mountain Biological Laboratory. And they looked at a potential case of a phenological mismatch in American robins. So at this field lab, they've been recording the arrival dates of robins since the 1970s. And so that's kind of what this graph is showing on the right-hand side. And what they saw is that those birds began arriving earlier and earlier and earlier. So the date of first sighting that you see on the y-axis, that's just a number that corresponds to a day of the year. So 1 is January 1st, and then so on and so forth from that. So you can see in this late 70s, there were birds that were after day 100, almost a day 105, but by 1998, there were birds that were, coming back almost a month earlier. And what they saw is that the American robins were arriving at elevations before the snow had melted. So they were taking that cue to migrate at a lower elevation and then applying that to what they thought the conditions were like at the higher elevation and getting there. And then suddenly they're not able to breed because the conditions aren't right for breeding. So now they've wasted a lot of energy going upslope to get somewhere where the conditions aren't right for breeding, where food is probably scarce. So they're either forced to burn more resources while they're there just to hang out so that they can claim the first territory when the females arrive. I don't know exactly if robins, if it's always the male that comes back, but first, but in a lot of birds, that is the case. So there's this mismatch. So the bird has to make a choice. Is it going to fly back down to a lower elevation, or is it going to hang out there and try to survive? And we've seen similar stuff like this here in Colorado Springs. So a couple of years ago, I want to say it was 2019, maybe, where we had a lot of Western tanagers in town because they came back early, or they came back at the same time, but the conditions weren't right at higher elevations. So they were kind of forced to stay at a lower elevation. And, I was talking to people who had lived in Colorado Springs for a long time and never seen a Western tanager. And they were asking me what this crazy bird was in their backyard. And I'm sure Michael's phone was ringing off the hook at the shop, people asking him what was going on with all the Western tanagers. But that's sort of an example of kind of a mismatch. And sometimes it's just random with weather, but if that mismatch persists, then it can have effects, population level effects, as we talked about earlier. So I'm going to try to explain that about what some of the theoretical basis for that is. So this is a graph, just conceptual graph, where you have food availability on the y-axis, and then whatever time it is during the breeding season on the x-axis. And so food availability is kind of this hump. And this is what it looks like in a lot of places, where at the beginning of the season, down here on the left-hand side, you have low food availability because either there's still snow on the ground or trees haven't leafed out yet, so caterpillars haven't started emerging, or something of that nature. And then as the breeding season progresses, you have this peak of food availability. And that peak of food availability is really important because that's what a lot of birds, most birds, try to sort of model their entire breeding season around, because they want the peak of that food availability to coincide when they need the most food. So using robins as an example, so at the beginning of the breeding season starts, a male shows up, starts singing to claim a territory. Shortly after that, if they didn't come together, a female pairs up with a male. They build a nest, or the female builds a nest in this case, lay eggs and have young. And now if they've done it just right, they've timed the peak of the food availability to be with the time that their nestlings need the most food and most energy, so they can get a good nestling weight. Higher nestling weight typically means higher chances of survival once you come out of the nest. Doesn't necessarily mean you'll have a better haircut, but you will be able to survive a little bit better. And then hopefully you make it past that nestling stage, become a juvenile, and then you are able to eat enough food to go off and migrate, and then return and start it all over again. Now, the problem comes if for some reason climate change causes a shift in that peak of food availability. So that hump kind of moves to one side or the other. So in that scenario, again, you have the male come back, he gets a female, they lay their nest, maybe it's a little early, they're still able to hatch their eggs, but they're not able to find enough food. So they don't have any fledglings, so they don't have any juveniles that survive to make it into the breeding population. And that's sort of the fundamental model for why a lot of scientists think that climate change can disrupt this phenology. So in some cases, like in the robin example that we have here, there's this mismatch in they're cued to migrate early, they get to the higher elevation, and because there's a mismatch between the changes in the climate at the higher elevation versus at lower elevation, then they're potentially arriving too early. In other cases, it might shift the other direction at lower elevations, where you have birds maybe that leave the tropics too late and they arrive and then they miss the peak, because now the peak of that food bump is too soon, that they've nested too late to maximize that. And you see the kind of pattern repeated in a lot of places. And basically what that would do, if there is a substantial effect, is it would drive some populations low enough that they would either no longer occupy those areas, and they would have to shift their populations to different ranges, to a different range of geographic region in order to breed successfully, or they would go extinct in that location. Another example of something that's local, that I probably, if I would have had more time, I should have reached out to Dr. Linkart to get some more information about this, but they've seen this just up the road in flammulated owls. They've seen that in this case, the breeding season has actually advanced. It's a lot earlier. They've noticed that there's been lower numbers of offspring produced, potentially because of increases in predation by red squirrels. So there's potentially higher red squirrel populations for a couple of different reasons, some that are related to wildfire around their study sites, others that have direct links to climate change. And then they've also looked at this increased wildfire severity and a longer fire season. So flammulated owls can benefit from fire, low intensity fires that are in some of these mature ponderosa pine forests can clear out a lot of the understory and create spaces, this open understory that flammulated owls need in order to forage successfully and consequently breed successfully. There's still a lot that's unknown, but this is an excerpt from the Birds of the World account that Dr. Linkart wrote with another co-author who I'm not familiar with, McCallum. It was last updated in 2013, but they've definitely noticed a shift in the breeding phenology over the 30 years. So they've been, he's got an amazing data set, and they've definitely noticed advances and changes in response to climate change. The last example I wanted to show is related to greater sage-grouse. And one of the reasons I chose sage-grouse is that there is a lot of research on sage-grouse, but also they're not very good dispersers. They can move around great distances, but nothing, it's not like a flammulated owl that's migrating to Mexico, or lark buntings that are up and down the Front Range, and down into South Texas and into Mexico as well, or even some robins that are making big moves, even though they're shorter distance migrants. Sage-grouse are a little bit more constrained than a lot of these other species. And we know that temperature and precipitation are major drivers of both sagebrush distribution itself, so the habitat component that they need, as well as just the population dynamics of grouse. So if you look at the top graph, this is from a study in Nevada. This is not Colorado, but definitely relevant to Colorado. It's looking at male recruitment as that's related to rainfall. So male recruitment is just a juvenile that survived after it was born for the first year and is able to enter the breeding population the next year. So it's a really important factor for maintaining a stable population. So the dark line is that recruitment level, and that dashed line is rainfall. And you can see there's a really tight relationship, particularly in very high rainfall years where you have very high recruitment, but even in lower rainfall years, that line, the recruitment line, tracks the rainfall line pretty well. For annual survival versus temperature, so that's the bottom graph. So the bottom one, the solid line is male annual survival. It's just the proportion of males that are surviving versus temperature, which are the average maximum temperature during that year. And you can see that they're inversely related. So the cooler it is, the higher survivorship you have, and the warmer it is, the lower survivorship you have. So when you start looking at these scenarios for both increased temperature and increased drought, it doesn't look good for sage-grouse. There is some anticipated shift, and there's multiple sources that think this is going to happen. There's going to be some shift in the sagebrush community that will be able to go a little bit north and a little bit upslope, but it's a little bit. It doesn't seem like it's going to move that quickly. A lot of the sagebrush takes a long time to grow. So you're back to that problem where you have an increase in temperature that typically took thousands of years that's now going to take place in a couple of decades. So you're going to run into that problem as well. There's also evidence that the change in the climate is going to increase the suitability for West Nile virus, which also can have an effect not only on sage-grouse, but on other birds and humans as well. And then with all of that, it kind of, they have a lot of things being thrown at them, is this increase in wildfire risk and invasion of cheatgrass, which is a non-native grass that doesn't play nice with sage-grouse. Not only is it when it does burn very quickly and very hot, so it destroys a lot of sage-grouse habitat when a fire does go through there. They've looked at all sorts of interactions with sage-grouse, and pretty much anytime there's sage-grouse present with cheatgrass, no matter what they look at, the numbers are lower. So they have lower survivorship, they produce fewer offspring, and their offspring don't have as high a chance of surviving either. So this is just one more map, kind of looking at sort of the heart of greater sage-grouse habitat. So you can see Denver is in the lower right-hand corner there. So that's where Colorado, and then to the west of there, you got Utah, and then to the north, Wyoming, Idaho, and Montana up there. And on the far western side is Nevada. So this is kind of like the stable area, the current distribution, with a small increase in temperature. You do see a pretty substantial loss, especially in the Great Basin area. You do see this sort of, I don't know if you can see my pointer or not, you do see this migration of some of the habitat upslope. But as I mentioned, it doesn't go upslope very far at all. So there's some gains there that might offset some of the losses. But when you start looking at the warmer scenarios, there's a pretty decent chance that sage-grouse may not be around, even in the state of Colorado, except for holding on in a few areas. All that being said, it may not be all bad news for all birds. Some birds are probably likely to benefit from a longer breeding season, which is what climate change probably means for some of those species that can handle slightly warmer temperatures in the more southerly portions of the United States, and birds that are capable of multiple successful nests per season, the so-called double-brooded species. It might really benefit them too, because that's going to give a longer breeding season potentially, so that they have higher chances of pulling off multiple broods. There's also something that they talked about this in the Fort Collins meeting last week. There's a lot of uncertainty about species interactions, and most of the models that you look at, climate change models, don't take that into account. So some species, as their ranges are shifting, some are going to shift one way for one reason, maybe, and maybe they're both in the general direction, but now you have overlaps that you didn't have before. So those species might encounter more competition for resources. In other cases, you might encounter reduced competition. So if a species is able to move upslope, for example, where it kind of moves away from those traditional species that it might be in competition with, they might then gain an advantage. A lot of that stuff is largely unknown, and I think maybe the next decade or so we'll probably understand a lot more of that as we see those interactions taking place. But for now, that seems like kind of an unknown thing that these models aren't taking account for. There was a recent study that looked at drought and tree mortality in the Sierra Nevada, and they actually found some surprising results, that a large portion of the avian community, if 47%, had a positive relationship with the temperature increases they observed during their surveys, compared to 20% that responded negatively. So some of the species that responded positively during their surveys were the lazuli bunting, national warbler, warbling vireo, and hermit thrush. And there was a whole additional list, but just as some that jumped out at me. But more species did decline with drier conditions than increase. So even among everything that they looked at, it seemed like that those drought conditions still seem to drive a lot more of the population dynamics than maybe temperature alone. So what can we do? This one was a hard slide to make. It does seem like that the highest temperature increases are the most likely. Maybe not the full temperature increases, but at least trending towards those higher temperature increases. There's a few things I think that we could advocate for in terms of planning purposes and conservation purposes. And some of this is already being done. It is kind of hard to implement, but if we can push for increased habitat connectivity, that's going to allow these long-term migrations and shifts in habitat distributions. It's going to give more room for error. So if we can conserve, as opposed to just conserving the top of a mountain or something adjacent to the bottom of the mountain, if we could conserve a corridor going all the way from the bottom to the top, those are the types of things I think that could be effective at mitigating some of the issues related to those shifts. Another thing we could do and should always do, I think, is increase habitat resilience by promoting fire-wise practices. This includes forest thinning and reducing the cover of some trees, which I know is often a controversial issue, because we don't, there's always, well, they thinned too much or they didn't thin enough. It is kind of an eyesore, especially right after it happens. But if we can implement those practices in places that could potentially stop a catastrophic wildfire from burning down the entire forest. I think those are the types of things that could help increase resiliency. And then another one is just reduce bird mortality from non-climate threats. So bring your cats inside, do what you can to help reduce building collisions, whether it's your own window or talking about really pushing some of these lights out initiatives that are taking place across the country, enhancing your backyard as a bird habitat, just so that there's more places for birds to live. And that all gets back to sort of this push that came out with 1 billion birds lost, which is a 7 simple actions to help birds. So drink shade-grown coffee, reducing plastic use, be part of citizen science. It mentions the making windows safer, keeping your cats indoors, native plantings, and avoiding, pesticide use. Those are all things that can help bird populations now, which hopefully will give them, some sort of buffer for their populations should they, need to adjust in response to climate change. All right, so that is the end. I will try to take questions. I'm not a climate expert, but I spent an inordinate amount of time reading about birds and climate, so I can try to field any questions that folks have.